A little bit of history. Tycho Brahe lived between 1546 and 1601. He came from a wealthy Danish noble family and sought to improve the accuracy of the observations of planetary motion available at the time. Brahe committed himself and his resources to recording the positions of the planets 10 times more accurately than had been done previously. Using money and resources given to him by the King of Denmark, who was grateful for having his life saved by Tycho's uncle, he built an observatory with large and accurate instruments on an island made available to him by the king. Tycho Brahe worked before the invention of the telescope, yet he still managed to measure the positions of the planets to 1/60th of a degree accuracy. Brahe believed that the Earth was at rest, with the Sun orbiting the Earth and the other planets orbiting the Sun, an intermediate picture between the Ptolemaic system and the ideas of Copernicus. Johannes Kepler, who lived between 1571 and 1630. Kepler, who started working with Brahe in 1600, accepted Copernicus's view of the solar system. The two did not get on. Brahe was suspicious of his student and afraid that he would overshadow his reputation in astronomy. As a result of this, Brahe set Kepler the difficult task of understanding the orbit of Mars, in the hope that it would keep Kepler busy. The difficulties with the orbit of Mars were due to it being the most elliptical of the orbits of the planets for which Brahe had data. It was this data that was key to the formulation of Kepler's laws of planetary motion, for which he is famous. After Brahe's death the following year, Kepler continued to work on Brahe's data. Kepler's first 2 laws of planetary motion were published in 1609. They are the law of orbits, that all planets move in elliptical orbits with the Sun at one focus, and the law of areas, that a line that connects a planet to the Sun sweeps out equal areas in equal times. Kepler's final law was formulated in 1618, and it is the law of periods. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. You can see here there is a diagram which shows r, the semi-major axis of an elliptical orbit. In terms of complete orbits, elliptical orbits can be treated as circular, as the period of an elliptical orbit with a semi-major axis of r and a circular orbit of radius r, as shown in the diagram, are the same. A planet in an elliptical orbit moves faster when it is closer to the Sun and slower when it is further away. A body in a circular orbit, however, has a constant speed. A circle is, in fact, geometrically just a special case of an ellipse. According to Kepler's law of periods, for any 2 satellites, 1 and 2, orbiting the same body, r cubed over t squared is a constant. So r cubed 1 over t squared 1 equals r cubed 2 over t squared 2, where r is the radius of the circular orbit, or length of the semi-major axis of an elliptical orbit, and t is the period for a complete orbit. A graph of r cubed against t squared, where r cubed is in kilometres and t squared is in days for the planets of the solar system, yields a straight line, as is predicted by Kepler's third law.